Hi, everybody. This is Dr. Nigro with the second of our screencasts for our notes on circular motion. This screencast is going to focus on centripetal motion and centripetal acceleration. All right, so that's a new word for us, centripetal. So that word was actually derived by Sir Isaac Newton, he of the motion laws and calculus, and he derived that based on some words from Latin. All right, if you split the word in half, centri comes from centrum, which in Latin means center, and then petal comes from petos, which means seeking. All right, so centripetal means a motion that is center seeking. All right, and so what does that really mean? Well, if you think about driving in your car and if you go around a tight curve, you will find yourself leaning towards the center of that curve because your body is seeking the center of that circle of which the curve is a portion of. So any motion that has the force and acceleration pulling you towards the center of the circle is called centripetal motion. Now, there's another word out there called centrifugal, which is the opposite. It's the outward seeking. All right, but we aren't going to be dealing with centrifugal motion, just centripetal motion. All right, so here I have a picture of a tennis ball that's moving in a circular path. The blue arrow shows you the direction of motion. All right, and as this tennis ball moves around the circle, is it accelerating? All right, well, you don't know the velocity, but even without knowing the velocity, we should be able to answer this question. All right, and the answer is yes, of course it's accelerating. As you move around a circle, you are always changing your direction. All right, and if we're changing direction, then our velocity is also changing. All right, and we know that things with changing velocity have acceleration. All right, so any object moving in a circular path has to be accelerating, no option. And because of that, we've got changing velocity, which means acceleration. All right, so let's talk specifically about centripetal acceleration. So you note that I've got this little c here. All right, it's not vital that you include that when you do your calculations. However, you're going to see the formulas for centripetal acceleration are different than the acceleration formula we used in the past. So I tend to put it there just as a reminder that we should not be mixing our formulas. All right, so centripetal acceleration is defined as the acceleration of an object that's moving in a circle. All right, we'll come back to the formula in just a second. Centripetal acceleration is always perpendicular to the velocity, and that centripetal acceleration always points to the center of our circle. All right, so if we have a circular path like this, here's the center of our circle, and we have an object out here, for example. All right, as the object moves around the circle in this direction, all right, it's going to have different points on the circle. So let's put it over here. All right, the velocity of your object is always tangent to the circular path. So it means it kind of moves like this. All right, at any given point on that circle. Now, the acceleration or the centripetal acceleration, no, it's always perpendicular to that, so it always points in towards the center of the circle. All right, so we'll have a right angle between these two values at all times when the object is in circular motion. All right, now how do we calculate centripetal acceleration? All right, before we would look at the change in velocity and divide that by time. All right, for a circular motion, it's a little bit different. That centripetal acceleration is going to be equal to our velocity value squared divided by the radius of our circular path. All right, so you can see that this calculation looks very different than what we did before, but that's okay. We'll get used to using it. A lot of what we're going to be doing is going to be circular in this unit, so we'll be using it quite a bit. All right, so to get a little bit of practice, we're going to try these two problems. All right, a go-kart travels in a circle with a radius of 35 meters. And if the cart has a speed of 3.75 meters per second, what is that cart's acceleration? All right, so let's look at what we know. All right, we have a radius of 35 meters and we have a velocity of 3.75 meters per second. All right, well, I know that centripetal acceleration is that velocity value squared divided by the radius. So 3.75 meters per second squared divided by 35 meters. All right, if we plug that in, we are going to find that our centripetal acceleration is equal to, hold on, 0.4 meters per second squared. So that is the centripetal acceleration of our object cart here as it moves around that circular path. All right. Now, these next two questions are going to look at the relationships between these variables. All right. So if you see that radius value is in the denominator of our formula. All right. So if it changes, the acceleration is going to change in the opposite direction. So for our first example, that radius, what if I doubled the radius? So now the circle is twice as big. All right. What is that going to do to our acceleration? All right. So if I increase that radius by 2, all right, then I'm going to see a decrease in my acceleration by the same amount, by a factor of 2. So it'll decrease 2 times. So in other words, the acceleration will be half of what we saw before. All right, so those two are indirectly related. As one goes up, the other goes down. All right, well, what if instead we're looking at the velocity? All right, the velocity is in the numerator, so the velocity and the acceleration are going to work together. As the velocity goes up, the acceleration is also going to go up, which makes sense because if you increase the speed, then the acceleration is also going to go up. All right, well, in this example, we're going to decrease the speed. So the velocity is going to go down by half, which is like decreasing it by a factor of 2. All right, which means the acceleration will also go down because they work together. All right, the issue here is this square that we have in the formula. So whatever the velocity does, we need to square it, and then that's what's going to happen to our acceleration. So our acceleration in this case is going to go down 4 times. All right, so whereas before the acceleration may have been 1, now it's going to be 1/4 of what it was before. All right, and again, that's because we have a direct relationship between acceleration and velocity. But that velocity value is squared, so that means we need to square what's going to happen to our acceleration. All right, let's look down at problem number 2. All right, we have a speedboat that travels in a circle with a radius of 12.5 meters. If the centripetal acceleration is 3.25 meters per second, what is the boat's velocity? All right, so we have a radius value of 12.5 meters. We have a centripetal acceleration of 3.25 meters per second squared. And this question wants to know the velocity. Well, I know that centripetal acceleration is equal to v squared over r. All right, so if I plug in my values, 3.25 meters per second squared for my acceleration, v squared for that velocity, and then 12.5 meters for my radius, I'm going to end up having to take the square root of both sides, which would be 40.6 meters squared, second squared. I'm going to find that my velocity value here is in the ballpark of 6.4 meters per second. All right, so if I have an acceleration of 3.25 meters per second squared, and the object is moving around a circle that has a radius of 12.5 meters, then I have to be going at a speed of 6.4 meters per second. All right, so now it wants to know how long does it take the boat to go around the circle one time. All right, so this one time tells me I'm looking for the period of this motion. And I remember that velocity is also equal to the circumference over the period. All right, so if I plug in my 6.4 meters per second for that velocity, and 2 times pi times my radius of 12.5 meters, and divide that by my unknown period, I can use my calculator to do some math, move the period to the top, divide both sides by the velocity, and the period for this motion is 12.3 seconds. So moving at this speed with this acceleration around this size of a circle it's going to take me 12.3 seconds to get around one time. All right. And then finally, what is the frequency of this boat in hertz? So again, hertz is the same thing as a revolution per second. And I have seconds already, so I don't do any unit changing. And the frequency is equal to 1 over the period. So in this case, 1 over 12.3 seconds, that frequency is going to be 0.081 hertz. All right, so I'm going to be able to move 0.081 part of the circle every second. Okay? All right. So that is what we're going to do with centripetal acceleration. Come back and we'll talk about centripetal force.